Schrödinger was a man born in 1887 in Austria and won the Nobel Prize in 1933 for his now famously known Schrödinger wave equation, leading to the foundation of quantum physics. Now let me ask you a question. What is the most famous equation of all time? You have guessed it. It has force equal to mass times acceleration. Why is this so popular, you might think? Well, can you eat it like Oreos? No! Why would you eat it? It's a thing that measures. It helps to predict the momentum and position of any object at any time. But wait, I have bad news. Second law, or force is mass times acceleration, doesn't work in quantum mechanics because it only deals with big things, like apples and stuff. But quantum mechanics deals with small things, like only subatomic particles, like electrons, photons, and neutrons that make up the atoms in an object. But wait, there is a replacement for F equals ma in quantum mechanics, Schrödinger's wave equation. Unfortunately, again, it is very hard. Some people even think it's the hardest thing in the universe. Yeah, there are more things that we wonder about, but it's very hard. But now I have derived a slightly easier way to derive it. Have fun with your new derivation, and thank you. Now let's get on to the math. Now we will do the math of the time-independent Schrödinger equation. Energy is potential energy plus kinetic energy. Let's see. So the equation for kinetic energy is half mv squared, and p is just replaced by u. So p half mv squared plus u. Wait, does anyone notice something? P is mv, right? Okay, so let's whole square both sides first. P squared is m squared v squared. P squared, m squared, v squared. Now divide both sides by 2m. So to m goes to m squared, m times. So p squared over 2m is half mv squared. Okay, so we're going to replace half mv squared with p squared over 2m. We'll see why, okay? Okay, next part 2. Psi is equal to e raised to the I kx minus omega t. Omega. You get it as in omega flowery. So let's take the derivative of psi. Psi of dx is equal to ik times e raised to the I kx minus omega t. But e raised to the I kx minus omega t is the same as psi. So d psi over dx is equal to ik times psi. Now let's take the second derivative of psi. D squared psi, or dx squared, equals to ik whole squared times psi. So, d squared psi over dx squared is I times psi. But wait, I is just not any variable or something. It's an imaginary number. Its value wasn't known until scientists wanted to set a value for it. The square root of -1 is I. So I squared must be -1 square root of -1 squared. But the square root of -1 is I, right? But the square root of -1 will square root to -1, right? But if we square -1, then that reverses it. So they eventually cancel out. So I squared is -1. Okay. Now you get it. Let's say dx squared is -k squared times psi. But wait a moment. We can't do anything with this. In order to do so, we have to find the value of k. So, let's see. Let's make a separate room for that. K is 2 pi over lambda. But we can't just run away with that. We have to go through a long process first. Not really long, but I'll say long. So, k times lambda is lambda k, and 2 pi times 1 is 2 pi. So lambda k is 2 pi. And if you don't know what that's called, it's cross multiplication. When you have an equal, not a times sign. You usually use fractions to multiply. And you multiply one number by its diagonal. So k times lambda is lambda k, since they're on the same diagonals. So lambda is 2 pi over k. If you clearly isolate lambda by dividing both sides by k, a different one. This is what I call de Broglie, or the Broccoli's hypothesis. So, lambda is h over p. If you already know what cross multiplication is, then you should know what to do on this part. Lambda p is h. So p can be simplified. P will be h over lambda. Simplified to h over 1 times 1 over lambda. Or again simplified as h times lambda raised to the -1. P is h times lambda raised to the -1. The value of lambda is 2 pi over k, right? Since there's a -1, that we're going to flip it. H is k over 2 times k over 2 pi. So p is 8k over 2 pi. But wait a second there. H is over 2 pi and reduce Planck constant. So reduce Planck constant to k. But we're trying to find k, not p. So supposedly by isolating k, by isolating k, by dividing both sides by reduced Planck constant, we see that k is reduced Planck p over reduced Planck constant. Okay, equals all the space down here. Whew. It has been a long time, hasn't it? But never give up, okay? E squared psi over dx squared is negative p squared over reduced Planck constant squared times psi. Now let's put reduced Planck constant squared on both sides. Reduced Planck constant squared p squared psi over dx squared equals to negative p squared over reduced Planck constant squared times psi. Reduced Planck constant squared. Cancel, cancel. D squared psi over dx squared is equal to, time reduced Planck constant squared is equal to negative p squared psi. And that is the end of part 2. Pretty long, right? Well, at least the third part is short. Okay, so now we have to use this information and this information to do the final part. Yeah. E is p squared over 2m plus u. Multiply everything you literally see right now on your paper by psi. And you should get this. Psi is p equals psi over 2m plus psi u. Wait! Exception here. D squared psi over dx squared times reduced Planck constant squared on negative p squared psi, right? Since it's positive, then d squared psi over dx squared times reduced Planck constant squared should be negative. So psi e is negative d squared psi over dx squared times reduced Planck constant squared over 2m plus psi u. And that is the time-independent Schrödinger equation. I'll do the time-dependent a little later. Now we are starting the time-dependent Schrödinger equation. If you haven't watched the proof for time-independent Schrödinger equation, go watch it now. Anyways, let's start from the first. Let's start from the first line. E is reduced Planck constant times omega. So psi is equal to E raised to the I kx minus omega t. D psi over, why is it so actually? D psi over dt is equal to I omega with respect to t, omega t times psi. Now, let's use E equal to reduced Planck constant times omega again. Let's multiply everything you see on the paper right now by psi. So now divide everything by reduced Planck constant. I'm not joking. Reduced Planck constant cancel. So psi e over reduced Planck constant is psi omega. Now let's put negative I on both sides to t. So that is d psi over dt. So now let's multiply both sides by negative I. So psi. Okay. So I forgot to mention that negative I over Planck constant times psi. negative I squared, and h cancel from the line. Negative I squared times psi e equal to d psi over dt times negative I8 is equal to d psi over dt minus times minus I with the constant. So we will replace let's take the Schrödinger equation. D psi over dt times negative I8. So that is equal to, also, I forgot, it was positive, not negative. Okay, so I'm looking forward. So negative, positive. Okay, we're good here now. So d psi over dt times with I times the Planck constant is equal to negative d squared psi over dx squared times the Planck constant squared over 2m plus psi u. Anyone remember that from the time independence equation? I hope you do. Anyway, that is the time dependent Schrödinger equation. Hello, my name is Sabrina Isaac Berry. I'm from Berry Science Lab. Schrödinger wave equation. Let me tell you a story. The Schrödinger wave equation, invented by Austrian physicist Erwin Schrödinger, he won the Nobel Prize in 1933. The Schrödinger wave equation set the foundation of quantum physics immediately. Bad news is that quantum physics is kind of hard, and Schrödinger's wave equation is even harder. So now, let me ask you a question. What is the most famous equation in the entire universe? You guessed it! It is Newton's second law. F is ma. So, why do we love F equals ma so much? You ask, can we eat it? No way! So why do we love it so much? It can explain the future of object. Yeah, the momentum and the position of just one object. Unfortunately, Newton's law doesn't work in quantum mechanics because quantum mechanics is only the law of small things, such as protons, electrons, and neutrons. And that's the end of my story. Now, I'll show you the math. Also, I forgot to mention that there are two kinds of Schrödinger wave equations. Number one is time-independent Schrödinger wave equation. Number two is time-dependent Schrödinger wave equation. Right now, we're doing the time-independent Schrödinger equation. So, energy is kinetic energy plus potential energy. Kinetic energy equation, as you know, is equal to half mv squared. And then PE is replaced with U, or momentum is mv, right? But let's take a bit of a walk here. Let's whole square both sides. P squared is m squared v squared. Now divide both sides by 2m. M goes to m squared m times. So p squared over 2m is half mv squared. So E is p squared over 2m plus u. Now basically we're using all the substitutes we could find. Okay, so now that part 1 is done, let's do part 2. This is going to be the longest part. I is e raised to the I kx minus omega t. Let's take the derivative side. d psi over dx is equal to ik times e raised to the I kx minus omega t. But e raised to the I kx minus omega t is equal to psi, right? So we can use that instead. Now let's take the second derivative, which leads us to even more math. D squared psi over dx squared. So d squared psi over dx squared is equal to ik whole squared times psi. Now ik whole squared actually means we square both of them, as shown in the last problem. I mean in the last part, where we whole squared p and mv, and then after we whole squared mv, we got m squared v squared. So d squared psi over dx squared is equal to I squared k squared times psi. But wait, I is actually an imaginary number, actually defined until it was found by scientists. So the value of it was -1. I is the square root of -1. That means I squared must be equal to the square root of -1 whole squared. But square root and square root cancel, which means that -1 remains. So I squared is -1. So d squared over d squared psi over the x squared, okay, is equal to -k squared times psi. But wait, we need to do something in order to continue our second derivative. Now, in order to continue our argument, we must stop for a minute. Now, we have to find k. So k is 2 pi over lambda. Now, we cannot just run off with just this explanation. We have to go through a long process. Not very long though. First, let's do cross multiplication. Lambda k is 2 pi. Also, if you haven't heard of pi before, it's an irrational number. We round it to 3.14, or to be infinitely precise, we just use the symbol pi. Pi is like this. It's like a line, but with two little tails curling under it. So now we bring k to the other side, since we want to find lambda. And so lambda is 2 pi over k. Now let's use de Broglie's hypothesis, or de Broglie means the broccoli. You get it, bro. You get it. It's funny jokes, right? So, lambda is h over p. That's the hypothesis. Now let's do cross multiplication. Lambda p is h, but we want to find p. So p is h over lambda. So that is h times 1 over lambda, or h times lambda raised to the -1. I'm saving space, okay? Okay. So let's stop there. Now, what is lambda? That is equal to 2 pi over k. since since there's a -1 here, we have to flip it. So 8 times k over 2 pi, which is just hk over 2 pi. But if you ask me, h over 2 pi is reduced and constant, which looks like 8, but there's a bar on its pole. So that's reduced and constant k. They call it h bar abbreviation. Psi over dx squared is equal to negative p. Wait a second, but p is equal to reduced Planck constant times k, right? But we tried to find k, so that is p over reduced Planck constant. So that's negative p squared over reduced Planck constant squared times psi. Now let's put reduced Planck constant squared on both sides. Reduced Planck constant squared d squared psi over dx squared times negative p squared over h equal to negative p squared over h squared times psi, and put a reduced Planck constant squared there. Cancel. D squared psi over dx squared times reduced Planck constant squared is equal to minus p squared psi. And that is the end of part 2 over 2m plus psi plus u. If you haven't seen, it is right here. That circle on there, you see? It's right there. Right there. Now, let's multiply everything by psi. You know what hit your buddy? Psi hit you. D squared psi of 2m plus psi u. So, psi, wait, p squared psi. But it states here that d squared psi over dx squared times reduced Planck constant squared is a negative p squared psi. So positive p squared psi must mean the negative goes to the other side. So let's write that. Psi e is psi over dx squared times reduced Planck constant squared over 2m plus psi u. And that is the time-independent Schrödinger equation. That was a lot of work. Now let's do the time-dependent. E is reduced Planck constant omega. Psi is e raised to the I kx minus omega t. Okay, so let's take the derivative of psi. D psi over dt, since it's in control of the next part now. I omega since times psi. E is reduced Planck constant times omega. Okay? Now let's multiply both sides by psi. Psi e is psi reduced Planck constant omega. Now let's divide everything by 8. Psi e over 8 is psi reduced Planck constant omega over 8. Oh, I forgot. They were reduced too. So 8 cancels. So reduced psi e over reduced Planck constant is psi w over psi double. Okay, now let's multiply both sides by I. Okay, so let's see. Now we have, okay. So let's multiply both sides by negative I now. Negative I over reduced Planck constant times e. Psi e is equal to negative I psi omega. I forgot to put a psi here, so I'll do that now. So let's replace it now. Negative I over reduced Planck constant psi e is negative d psi over dt, since this thing is all negative. Oh wait, it's it's negative, so it's positive. So let's see. Actually, it's negative I times reduced and constant times negative I over reduced and constant times psi e is equal to d psi over dt times negative I8. Okay. Phew. We don't need to back up a bit. We're perfectly fine. So, okay, so H cancel. Negative I squared times psi e is d psi over dt times negative I8. Well, wait a second here. Negative I squared. That's the I has a value of the square root of negative 1. So that's the negative of negative 1 squared. Squared cancel, and negative plus. So that's just 1 or nothing, and basically in multiplication. So psi e is equal to d psi over dt times negative I8. So let's use that instead of psi e. D psi over dt times negative I8 is equal to, write that down. Psi over dx squared times reduced plan constant squared over 2m plus psi. And that is the time-dependent Schrodinger equation. We did part 1 like an hour ago, and we reviewed that. So now let's review part 2. We found a new letter, psi, but we learned that it also had an exponent. It had a value of e raised to the I kx minus omega t. We took the derivative of psi, and we found out that it was ik times psi itself. The value of psi, well, then we took the second derivative of psi, and we found out a lot after that. We did de Broglie's, or should I say, the Broglie's hypothesis, which is lambda equals h over p. We found out that k was 2 pi over lambda, but to be precise, it was actually p over reduced Planck constant. And we also found out that reduced Planck constant was 2 pi over k. We discovered a lot in part 2. But part 3 was even more chaotic. We got the end of part 1 and placed it here. We put the law of part 1 and plugged it to there. We multiplied everything by psi, and then we stated that negative p squared psi was d squared psi over dx squared times reduced Planck constant squared. And since it's positive, the other sign must be negative. So, and that led us to the time-independent Schrodinger equation. We did a lot in the time-dependent, but that's just boring. So thank you for watching. I hope this video inspired you to fall in love with math and science, and hopefully subscribe to our channel, Berry Science Lab. E equals to negative d squared psi over dx squared times reduced Planck constant squared over 2m plus psi e equals to negative d squared psi over dx squared times a reduced Planck constant